Have you ever looked up, truly looked up I mean, gazed at the vast expanse above your head? You probably asked a simple question then. Why is the sky blue? It seems like such a straightforward query. But the universe is rarely that simple, is it? The answer to this common question is quite amazing. It involves the light from our nearest star, the sun. It involves the very air we breathe every day. We need to understand a little bit of physics. And we also need to touch upon some chemistry. These two sciences work together, you see. They collaborate to paint our sky that familiar blue. Think about the journey of sunlight. It travels 93 million miles to reach Earth. Then it hits our atmosphere, a thin layer of gas. This atmosphere is where all the magic happens. It is here that sunlight meets matter, and this interaction is key to the sky's color. So, let's embark on this scientific journey together. Let's unravel the mystery of our blue sky. Prepare to be amazed by the science above us. Sunlight. It bathes our planet in warmth and light. It appears white or perhaps slightly yellowish. But is it really just one color? The answer, my friends, is a resounding no. White light is not as simple as it seems. It is actually a mixture of many different colors. Think of it as a team of colors. All working together they appear as white light. Sunlight holds all the colors of the rainbow. Yes, the very same colors you see after a rain shower. Red, orange, yellow, green, blue, indigo, and violet. These colors are all bundled together in sunlight. A prism can reveal this hidden secret. When white light passes through a prism, it separates. It splits into its component colors. This band of colors is called a spectrum. Our sun is constantly sending out this full spectrum. These different colors are different waves of light. Light travels in waves, like ripples on a pond. But these are electromagnetic waves. Each color in the spectrum has a specific wavelength. Red light has the longest wavelength of visible light. And then we come to blue and violet light. These colors have the shortest wavelengths. It is the key to understanding our blue sky. Our planet Earth is special in many ways. One of its most remarkable features is its atmosphere. Think of it as an invisible, gaseous blanket. This blanket envelops our entire world. It is a relatively thin layer, compared to Earth's size, but it is absolutely essential for life as we know it. It provides the air we breathe. It regulates our planet's temperature. And relevant to our question, it interacts with sunlight. This interaction gives us our weather and our sky's color. This atmospheric blanket is made of gases, a mixture of different types of gas molecules. There are also tiny water droplets and ice crystals, and sometimes dust, pollen, and volcanic ash particles. For the most part, these particles are invisible to us. We walk through them every day without noticing, but they are there, millions of them in every breath. These gases and particles are constantly moving, creating winds, clouds, and complex weather patterns. This blanket does more than just give us air. It protects us from harmful radiation from the sun. It acts like a shield, absorbing or deflecting some rays. It also traps some of the sun's heat. This is the greenhouse effect, keeping our planet warm. Without our atmosphere, Earth would be very different. Let's zoom in on the composition of our atmosphere. What are these gases that make up our airy blanket? The air we breathe is not just one thing, it is a mixture, a cocktail of different molecules. The two most abundant gases are nitrogen and oxygen. Nitrogen makes up about 78% of the air. Oxygen accounts for about 21%. These two gases together form 99% of dry air. The remaining 1% includes argon, carbon dioxide, and others. But for the blue sky, nitrogen and oxygen are the stars. These molecules of nitrogen, N2, and oxygen, O2, are tiny. Truly incredibly small, far too small to see with the naked eye, or even with a standard microscope. They are much smaller than particles like dust or pollen. They are even smaller than the wavelengths of visible light. This size difference is absolutely critical. It dictates how these molecules interact with sunlight. Think of them as minuscule obstacles in the path of light. But their small size gives them special scattering powers. These molecules are not just sitting still, they are constantly moving, zipping around at high speeds. They bump into each other, and into other things. When sunlight enters the atmosphere, it encounters these molecules. Countless tiny particles ready to interact. Section 5. The Great Scatter, introducing Rayleigh scattering. Imagine sunlight, that rainbow of colors, entering our atmosphere. It encounters the tiny nitrogen and oxygen molecules. What happens next is a phenomenon called scattering. Think of scattering as light bouncing off particles, like a ball hitting a wall and changing direction. But this is not just any kind of scattering. When light interacts with particles much smaller than its wavelength, a special type of scattering occurs. This was described in detail by a British physicist. His name was Lord Rayleigh in the late 19th century. Lord Rayleigh studied how light scattered off tiny particles. He developed a mathematical formula to describe it. His work showed something very important. The amount of scattering depends strongly on the wavelength of light. Specifically for particles much smaller than the light's wavelength, like our friends, oxygen and nitrogen molecules, he discovered that shorter wavelengths of light scatter much more effectively than longer wavelengths. This crucial discovery is known as Rayleigh scattering. The key takeaway is simple: short waves scatter big. Section 6. Why blue wins the race, the scattering effect in action. We have established that blue light scatters more, thanks to Rayleigh scattering and those tiny air molecules. So what does this mean for the light we see? When sunlight enters the atmosphere from above, the blue and violet portions of its spectrum start scattering. They are redirected by nitrogen and oxygen molecules, bouncing from one molecule to another, spreading out in all directions across the sky. Imagine billions of tiny blue light sources all filling the dome above us. So, when you look up at the sky on a clear day, you are not looking directly at the sun, hopefully. You are seeing this scattered sunlight. And because blue light is scattered so effectively, much more than red, orange, or yellow light, the light that reaches your eyes from all parts of the sky is predominantly blue. This scattered blue light seems to come from everywhere. That is why the entire sky appears blue. It is a beautiful atmospheric light show. You might ask, what about violet light? Violet light has an even shorter wavelength than blue. So, according to Rayleigh scattering, it should scatter even more. Why isn't the sky violet then? This is an excellent question. It has a few answers. Section 7. More than just blue sunrises, sunsets, and hazy days. Our sky is famously blue during the day, but it is not always blue, is it? Think about the spectacular colors of a sunrise or sunset. Suddenly the sky bursts into reds, oranges, pinks, and yellows. Where does the blue go? And why these fiery colors? The answer lies in scattering and the atmosphere. The path of sunlight changes, involving larger particles. Conditions change, leading to different visual outcomes. At sunrise or sunset, the sun is low on the horizon. Sunlight travels a longer path through a thicker atmosphere. This means more scattering. Blue and violet light are scattered away. They are bounced out of the beam of light. So what light is left? The longer wavelengths, reds, oranges, and yellows, these colors are scattered less effectively. They can penetrate the thick atmosphere more directly. They make it all the way to your eyes. This is why sunrises and sunsets appear reddish or orange. The blue has been filtered out by extensive scattering. The more dust or pollution in the air, the more dramatic. These larger particles can also scatter light, contributing to the intensity of sunset colors. Section 8. Chemistry's subtle hand beyond simple scattering. Physics, especially Rayleigh scattering, explains the big picture. It tells us why blue light is scattered more, but chemistry adds important details and nuances. The specific chemical composition of our atmosphere is crucial. Remember, it is mostly nitrogen and oxygen. These particular molecules have specific properties. Their size is just right for Rayleigh scattering of visible light. Their electron clouds interact with the incoming photons of light. This interaction causes the re-emission of light in different directions. That is scattering at a fundamental chemical level. Other chemical components in the atmosphere also play roles. Ozone, for example, is a molecule vital for life. It forms the ozone layer high in the atmosphere. Ozone is very good at absorbing ultraviolet radiation. This is a chemical interaction with light. While this absorption does not directly make the sky blue, it affects the spectrum of light reaching the lower atmosphere, and it protects us from harmful UV rays. So, atmospheric chemistry is constantly at work, modifying light and protecting our planet. Pollutants in the air are another chemical factor. Human activities release various chemicals into the atmosphere. Section 9. A universe of color, our blue sky in perspective. So there you have it, the story of our blue sky. It is a beautiful consequence of fundamental science. Sunlight, a mixture of all colors, arrives at Earth. Our atmosphere, a sea of tiny nitrogen and oxygen molecules. These molecules are expert scatterers of short wavelength light. Blue light gets scattered all around, painting our sky. Physics explains the how of scattering like Rayleigh's principle. Chemistry explains the what, the specific molecules involved and how other substances can modify the spectacle. It is a daily show, powered by our sun and our air. The next time you gaze upwards, appreciate this marvel. It is not just an empty blue space, it is a dynamic region of interaction. Light and matter dancing a complex, colorful ballet. And remember, this blue is specific to Earth's conditions. Change the atmosphere and you change the sky's color. This is beautifully illustrated by other planets. Mars, for instance, has a very thin atmosphere. It is also full of reddish dust particles.